Mathematics demands absolute precision. Every proof relies on rigid, unambiguous logic. But when you force that logic through the filter of human language, the precision starts to bleed. Everyday words carry double meanings, cultural baggage, and rhetorical noise. By the late 19th century, this ambiguity became a crisis. Mathematicians were attempting to prove the absolute bedrock foundations of arithmetic. They found they could not complete these proofs because the very language they were using to write them was too unstable. Gottlob Frege, a German mathematician, recognized the problem. He wanted to strip all linguistic embellishment and psychological baggage from logical proof. He realized that ordinary human grammar was entirely the wrong tool for the job. You cannot build a perfect mathematical structure using words designed for casual conversation. His solution was to invent an entirely new mode of expression. In 1879, Frege published a text introducing a lingua characterica, a purely formal, symbolic language modeled directly on arithmetic. In this 88-page booklet, Frege proposed a radical thesis. To construct a flawless logical system, mathematicians had to completely abandon the rules of human grammar. He argued that logic could no longer be treated as a subgenre of linguistics. It had to be completely rebuilt as a strict mechanical system for pure thought. For 2,000 years prior to Frege, formal logic was tightly bound to the rules of spoken language. The architect of this enduring system was Aristotle. His framework dictated how scholars analyzed arguments for millennia. The core mechanic of Aristotelian logic relies on sentence structure. To analyze a statement, you divide it into two parts: a subject that you are talking about, and a predicate that describes what the subject is or does.
This model breaks down when applied to a simple mathematical relationship like A is equal to B. Grammar forces A to be the subject and equal to B to be the predicate, creating a hierarchy that does not exist in the math itself. If we swap them to B is equal to A, the subject changes, even though the logical fact remains identical. Traditional grammar prioritizes the way we say things over the fixed relationship between the values. Frege discarded this entirely. He replaced the grammatical concepts of subject and predicate with the mathematical concepts of function and argument. By identifying human grammar as the primary obstacle to rigorous proof, Frege severed logic from the spoken word and aligned it directly with mathematical structure. Traditional grammarians analyze language by starting with individual words and stacking them to build a sentence. Frege worked in the exact opposite direction. He started with a fully formed thought. To understand its underlying logic, he systematically broke that thought apart through a process of mathematical decomposition. In his text, Frege demonstrates this method by comparing logical structures to chemical ones. He sets up a specific test sentence: hydrogen is lighter than carbon dioxide. To find the logical skeleton hidden inside those words, he applies a replacement test. The premise is simple. You alter the components of the sentence one by one and observe what survives the changes. Frege proved that you do not discover meaning by adding concepts together. You find it by stripping away the variable parts until only the invariant structure remains.
Let's look at this diagram. Here is our coherent thought before any manipulation. Frege's first step is to swap the word hydrogen for oxygen. The factual reality of the sentence has shifted because oxygen is heavier, but the structural relationship connecting the words has not changed at all. We can execute a second swap, replacing oxygen with nitrogen to confirm the pattern. The invariant part of the sentence, the phrase is lighter than carbon dioxide, is what Frege defined as the function. The replaceable slot, the gap where we swapped the different gases, is the argument. We can now transform the English sentence into its final mathematical notation, f of x. This decomposition process does not stop at a single gap. Sentences are rarely limited to just one argument. We can decompose the remaining text again by removing the second noun, carbon dioxide. We are left with a new state, a two-argument function, written as f of x and y. The function is simply the relationship is lighter than. This destroys the old grammatical rules completely. The traditional subject and object of the sentence have been flattened. They are now identical, interchangeable mathematical inputs. Notice that the function itself, the pure relationship, is neither true nor false on its own. Only when you plug specific arguments into those x and y slots does the function execute, outputting a final binary truth value, either the true or the false. This architecture transforms a thought into a system that evaluates the compatibility of specific inputs against a logical rule. This new architecture allowed Frege to solve a massive historical problem, leading directly to the invention of quantification theory. Ancient logic struggled to accurately express mathematical statements dealing with absolute scope, concepts like all things or some things. But because Frege mapped properties as functions, he could mathematically scale them. Look at this diagram. A new symbol, the universal quantifier, snaps into place next to the function. This notation precisely translates to, for all possible arguments, this function evaluates to true. Alternatively, we can use the existential quantifier to state the exact inverse. There exists at least one argument where this function evaluates to true. Because logical properties were now strict mathematical functions, mathematicians could accurately calculate the scope of infinite sets without ever relying on ambiguous human phrasing. This all culminates in the final achievement of Frege's book, the truth-functional propositional calculus. Here is what that pure language of thought actually looks like on the page. The notation looks entirely alien to human writing, and its design was strictly intentional. The core rule of this calculus is that logical derivations are carried out exclusively according to the visual, spatial form of the symbols. The process works entirely independent of what the symbols actually mean. In just 88 pages, Frege successfully replaced a system of logic tied to human grammar with one tied to mathematical necessity. By proving that complex thoughts could be reduced to symbols manipulated by rigid, formal rules, independent of human intuition, Frege established the foundation for formal systems. This shift made it possible to treat logic as a mechanical process, creating the conceptual blueprint for any programmable machine.